All right, folks, so we are chugging our way through this module, and we are getting very close to the point when this cartoon here is going to make sense to you, and it's going to be very, very exciting. But anyway, our focus continues to be, for now, on the linear regression equation, how we make those predictions that regression is so useful for doing. And we've talked for a couple of videos now about this linear regression equation, gone through some examples, but we haven't actually done anything with real data where we have to calculate those regression coefficients, the slope, which we call b, and the y-intercept, which we call a. So that's going to be the focus of this video. So the first thing we're going to calculate if we are actually trying to use data to create this equation is the slope, and you'll see why in just a moment. But for now, the slope has a pretty simple formula. SP divided by SSX. Now, you should remember you've seen both of those before. You've seen the sum of squares of x a great many times, starting all the way back in variability, I believe. And the sum of products showed up in the most recent module on correlations. So these are terms that we've seen before. And the formulas haven't changed. The sum of products, again, we have a definitional formula here where we're literally creating the products of deviations for both variables for every participant and adding them up. And then the computational formula here is designed to be a little bit quicker. We've seen those sum of squares formulas a million times too. Again, definitional formula here. Again, notice it's based around deviations. It's not that different than the sum of products. It's a similar logic. And then the computational formula here, which again looks pretty similar to the computational formula for sum of products. But here's the important thing. A lot of times we construct regression equations after calculating the correlation. If you've calculated a correlation, you already have both the sum of products and the sum of squares for x for the data set. So you can calculate the slope basically immediately if you've already done a correlation because you'll already have both the numerator and the denominator. Here's the important thing though, both of those things need to be right. If they aren't, you have a garbage in, garbage out problem happening. So double check your sum of products, your sum of squares for x when you're calculating this stuff, because it's important not just for the correlation and perhaps that hypothesis test, but also for a regression equation if I ask you to make one, which, spoiler, it's pretty likely I will. So if you read the book about this, they go into a little more depth here. They kind of veer away from how we talk about things. They describe using correlations and standard deviations to get the slope. We're not going to be doing that. Again, it's a perfectly valid way of getting to the same answer, but we keep it relatively simple and keep the formulas that we've been working with in the past and the things like sums of squares that we've been calculating. So again, there's going to describe an alternate approach, but we're not going to worry about that. So once we have the slope, we come up with a, which is the y-intercept, which basically means what's the value of your y variable, your criterion variable, when your predictor variable, your x, is 0. And again, we think of that as the anchor or the starting point of that regression line. So here's why we need the slope first. It's part of the formula for the y-intercept. We need that slope. We take the average score on y, on our y variable. We take the average score on x, multiply it by the slope, and subtract it from that average on y. So here's kind of a roundabout way of saying it. It's the mean of y minus the mean of x multiplied by the slope. That gives us the starting point. So that tells us our y-intercept or where things start. One note about y-intercepts, oftentimes they come up with really bizarre or sometimes even impossible scores. It doesn't matter. It's just giving you a starting point for the line. If it's way outside of the range of scores in your data set, oftentimes it will be kind of absurd. But the y-intercept can be positive, it can be negative. It's based, again, just on that slope and on the means of your two variables. So again, make sure your slope is calculated correctly or it's going to mess this up as well. It's going to mess up your overall predictions. So let's walk through a quick example before we wrap things up. Let's say that an educator is interested in figuring out what kind of reading materials to stock a new classroom with. Now the thing about classrooms, when you have an incoming class of students, you might not know much about things like their reading ability, but you almost certainly will know their age. So if we wanted to try to figure out appropriate materials for folks of that age, we might look at the relationship between age and reading ability in a sample, in this case 5 kids, in reality it'd be more like 5,000, and use that to predict the typical reading ability of different aged children. So we're going to be using this formula again. Again, our formula for slope involves the sum of products and the sum of squares just for x. We can get sum of products definitionally or computationally, and then we use that plus the sample means to calculate the y-intercept. So let's see what's going on here, and surprisingly you can get all the information you need from just these couple of extra columns here. Again, have an organization strategy for this. Have a plan, have it rehearsed enough so that on the exam you can sit down and just draw the grid and know where all the necessary information goes. So let's say this is our sample of 5 kids. We have their ages, they range from 3 to 7 years old. We have their reading ability on some measure of reading ability, ranges from 3 to 11. We're going to multiply x by y for each kid. We are going to need that for our sum of products. We are going to square each individual x and sum those up. We're going to need that for our sum of squares. And we're going to use that again and plug that into these formulas to calculate the slope. And we're going to use that and our means down here to calculate the y-intercept. So first we're going to calculate the slope, then we're going to calculate that y-intercept. Here is a completed data set, and again I encourage you to go through and just start with the initial scores and try to replicate this as just a little bit of practice with all the answers right in front of you. Repetitions are good in this course, especially to cut down on the error rate. But anyway, our x's add up to 25, which gives us a mean x score, a mean age of 5. Our y's add up to 30, which gives us an average reading ability of 6. We have xy, x times y for each individual kid. Added up, they add to 166. And then sigma x squared, each x score, each age squared, and then added up gives us 135. Those are all the numbers that we need, that plus the n, in order to solve the entire regression equation. So again, we're going to need to get a sum of products, a sum of squares for x, and that's going to give us our slope, which will then give us our y-intercept. All right, so we'll start with the sum of products. Sigma xy goes over here on the left side. Then here in the numerator, we take sigma y, multiply by sigma x, and divide by n. And again, importantly, n is the number of kids that we measured, which is 5. It's not the total number of scores. We wind up with a sum of products of 16. Pause there. What do you already immediately know about the correlation between these two variables? If you can't come up with an answer right away, what you know already is that it is a positive correlation. Sum of products determines the sign of a correlation. It also determines the sign of the slope. So because it's a positive correlation, we also know it has a positive slope. So if sum of products is positive, you have a positive correlation and slope. If it's negative, you have a negative correlation and slope. But moving on, sum of squares for x, we take our sigma x squared from this column here. We take our sigma x over here, and we square that, divide it by, again, the number of kids, and subtract. And you wind up with a sum of squares of 10 for our x variable. By the way, if you had calculated a correlation, you'd have sum of squares y and that sort of thing. You don't need it for this regression equation. So b, our slope, by the magic of made-up data sets, we have nice round numbers in both the numerator and denominator, and we get a slope of 1.6. What this is literally telling us is every time a child's age goes up by 1 year, on average, their reading ability goes up by 1.6 points. So on average, you age a year, your reading ability gets 1.6 points better. Then we're going to use that. We're going to use our two means, calculate our y-intercept. Again, our slope is 1.6. We multiply that by the average x. We get 8. We subtract it from the average y, which is 6. So we get a y-intercept of -2. That means that a 0-year-old child would have a reading ability of -2. Now, both of those are nonsensical. You can't really measure a 0-year-old child. It's pretty hard to get them the questionnaires, let alone get them to fill them out. And -2 probably isn't a score that's possible on the reading material. That's okay. That doesn't really matter as long as it's calculated correctly. Our predictions are the most accurate for kids who are inside of this age range or very close to it. The farther away you get, the more you can get wacky scores like that. So odd y-intercepts are pretty common. They're not anything to be alarmed about. Oftentimes we're projecting a score that's way outside of the scores we're actually dealing with, so we just wind up with weird y-intercepts. But either way, what it's saying here is a 0-year-old kid would hypothetically have a reading ability of -2, and every time that kid gets a year older, their reading ability goes up by 1.6 points. So here's our finalized regression equation. We multiply the slope by any x score that we choose to plug in, and then we subtract the y-intercept from that. Now you'll notice that the actual formula has plus a, but because it's negative, it winds up being a subtraction. You could have plus -2 in there, but it's too easy to trip you up. It's easier to make a mistake. You're simply subtracting 2 when you're adding a negative number. So let's say we got a 5-year-old kid coming in. What's their predicted reading ability? Again, we have our formula here. We plug in our x value of 5. 5 times 1.6 is 8. We expect them to be 8 points better than a 0-year-old child. But again, we add in that y-intercept of where a 0-year-old child would be expected to be. We subtract 2. 8 minus 2 is 6. Their predicted reading ability is 6. Now, on your own, try the same thing for a child of 4 and get their predicted reading ability. And then I want you to do something a little more unusual. Try and estimate my reading ability. I'm 40. That's my age. So what would my reading ability be according to this equation? And then plug it in for my dad. My dad's 69 years old. Plug that in there and see if you can figure out his estimated reading ability. Now here's the question to ask you, whether you get those results or not. How accurate do you think those predictions are and why? The answer should be it's hopefully pretty accurate for the 4-year-old kid, but it's probably not going to really be accurate for a 40-year-old or a 69-year-old. Why would that be the case? Well, you wouldn't expect reading ability to develop at the same rate for adults as it does for young children who are just learning how to read. What we've done there is something that we're going to talk about in our next and I believe final video, where we'll talk about extrapolation, estimating y-scores for values of x that are really far outside of your data set, like a 40-year-old person or a 69-year-old person when we measured kids that were 3 to 7 years old. We're going to talk about the problems extrapolation causes, and we are also going to discuss a little bit of the more advanced regression models and basically wrap up the module, the unit, and the course. See you there.